Hey, good afternoon, everyone, and welcome to our GReTA seminar this week. We have two speakers today, so two for the price of one. And the topic, as you can see, is graph databases. So you may think of, apart from being about graphs, what this has to do with graph transformation, but I'm sure that will be addressed in a moment. So I'm very happy to welcome Elvira and Fernando. They both have a long history of working in both logic and graph transformation, logic programming, algebraic specification, things like that. Fernando maybe a little bit longer than Elvira, but Fernando has been around since I remember, essentially, when I entered this field, which is also a bit longer now. So the work is on graph databases, but as you may appreciate, a lot of the problems, even if there's no transformation involved, a lot of the problems in graph transformation are about matching and expressing properties of graphs, even if they're not transformed. So all of that will also be relevant for graph transformation. But I let sort of Elvira and Fernando explain this, who I'm sure can do that better than I can. So I think Fernando will start and then Elvira will take over. Is that correct?
Yes.
Okay, so please go ahead and.
Yes, hello. Good afternoon. And yes, Raiko, I'm very old now. I've been around for a very, very long time now. Well, this time we are going to give this seminar about logic approach to graph databases. And actually, as you said, we are not going to talk about graph transformation, although many concepts from graph transformation that we learn in the context of graph transformation will show up in our presentation. But so to start, maybe, the contents of the talk. First, I will give a small introduction to graph databases, because maybe some of you don't know much about what a graph database is exactly. Then I will present the underground framework that we are going to use, so the kind of graphs we deal with for our work. Then I will present the logical semantics of a graph database, in terms of what is a query, what is a query satisfaction, and what are the correct answers to a query. Then Elvira will present the operational semantics and show the main result, which is the equivalence of the two semantics. And finally, I will draw some conclusion and show some future work that we are actually doing now. As I said, probably, maybe some of you don't know what is exactly a graph database, so it's very simple to explain. Graph database is just a database that is stored in a graph. So the database is a graph. And moreover, what it distinguishes that from other kind of databases is that from equational databases especially, is that queries are navigational, which means that you ask queries about connections in the database. For instance, here so what kind of graphs are considered to be the graphs that are, graph databases? What kind of graphs are? Well, they are called, the most standard kind of graph are property graphs, which are labeled multigraphs with properties, are called what we usually would call attributes, and with attributes on nodes and edges. There are several kinds of variations that people use in these property graphs. And also there's another model that is quite popular, but which is for us quite more ugly, which are RDF graphs. I don't know if you have heard about them, but so we are in the context of property graphs. So here you have an example of a property graph that shows the example that we are going to use along the talk. This is what is supposed to be. This is as a fragment of a database that include connections among cities and airports, so that one can plan a travel in the world. So you see here that edges they have as label their type typically, and so also nodes, the label is their type, what is considered to be their type, and you have attributes on edges, and etc. What is non-standard with respect to what we usually do in graph transformation is that nodes may have more than one label, which means that they may have more than one type. For instance, a standard example that in that area people shows is if you have a graph databases about films, about movies, then Clint Eastwood might be simultaneously an actor and a director of a movie. And so it would have these two roles, these two types. And the queries typically look something like that. So this the queries that we are showing are more or less close to the queries of the language Cypher or GCore or other similar query languages. So typically you try to match some specific patterns that may be just, in this case, you are matching an edge from a city to an airport, such that the name of the city is the same as the name of the airport, of the city associated to the airport, which is Los Angeles. And so we are asking for what kind of transportation we may have for going from the city of Los Angeles to the airport of Los Angeles. Then here you may be asking for a path. So this, when you have a regular expression in between an arrow, this means that we are asking for a path consisting of flights and shuttles from airport A1 to airport A2, and such that at the city of airport A2, there is a metro connection to the city. That's a subclause of this clause, etc. So in particular, in this case, you are asking for, in all this query, you are asking for some kind of connection from Los Angeles to Barcelona, having a stopover in some city in between, which is not defined which city, which is the A2 city, so it means that many possibilities can be possible answers to these queries. So the main problems that we decided why we started to work on this is that we found that there were not really logical foundations for graph databases, except for people studying complexity questions about graph databases. So this is the main work on logic associated to graph databases. And then also because we found that these property graphs that people were using are too ad hoc. For instance, dealing types with by means of labels is not very nice. And well, there are some other problems. So what we have done up to now is we have defined a formal model of graph or graph databases, which is essentially graphs, typed graphs, what we would call type attributed graphs, with inheritance on type nodes. Then we have defined a logical semantics for the query language, more or less a standard query language in terms of the language of the logic that we defined a couple of years ago, the GNL, graph navigational logic, and the connection to GNL actually is not only at the level, at the syntactic level and semantic level in terms of formulas and satisfaction. So the queries are just a fragment of the logic language, but also it happens that as we will see, that the operational semantics of the query language is actually defined in terms the rules of the logic. So it's similar to logic programming, or to similarly to logic programming. The denotational semantics are refutations of the queries that one has. Then, well, these operational semantics have been defined, as I said, in terms of the proof system, and then we have proved that both semantics are equivalent. So the rest of the contents of the talk is, first I will present you the underlying framework, then I will show you what are the queries and what is query satisfaction and what are the answers for a given query. Then Elvira will present you the operational semantics, and finally I will draw some conclusion. So let's go into the models, the kind of graphs we deal with. So as I said, we work with type property graphs, and we have called them that way, but this is, as I say, what we would call typed attributed graphs with no type inheritance. And this consists, as we usually know, of an untyped graph. Actually, an E-graph, I don't know, some of you may know what an E-graph is, some of you may not know. In a minute, you will see what it is. And then you have a type graph and a typing morphism for defining the types of the graph. So for instance, this could be the type graph of our example, of our running example, and this would be a fragment of the database, and the typing morphism will match nodes and edges from the graph to the type graph. So an E-graph is something that Iri with Ulrike Prange and Gabi Tenzer defined 20 years ago for working about with attributed graphs. And the idea is that one represents in a compact way in a graph everything, in the sense that not only are the nodes, the standard nodes and edges, but the values of the attributes are just considered as nodes. They are value nodes. And then the edges of the graph, in addition to the standard edges, so node properties are represented by an edge from a node to the value of the property or the attribute. And edge properties are represented by edges from an edge to also to a value. By the way, I'm using property and attribute in an equivalent way. I may use any of them. And then obviously we have source and target functions for all these kinds of edges. So for the normal edges, so the node property edges, and for the edge property edges. So for instance, this is an example of a E-graph. It already contains the types of the elements just for readability. So typically the types would come from the typing morphism. So in here, so we have this small graph consists of 2 nodes and an edge, and this node or the 2 nodes have an attribute which is the city of a given airport that is close to the airport, and the edge is has also some attributes, which are the airline, the ID of the flight, and the price of the flight. And as you see, these special edges are representing these attributes or properties. And that way, as I said, everything is in the graph. You don't need to have any kind of additional mapping from nodes and edges to attributes or something like that, as it was the case before. So before defining what is the standard, what is the type graph, that the kind of type graphs we use, let me talk about the types of nodes and edges that we assume we have. So we assume, since we are going to have inheritance on type nodes, we assume that we have given a partially ordered set of basic nodes, let it call it B and T, and a set of basic edge types, BET. And but these are not the only elements of the types. So the node types is actually the complete lattice generated by B and T, where meet and join are denoted by and plus. So this means that T and T prime is more or less a subtype of T and of T prime, and they are both subtypes of T or T prime. And we have a top and bottom that denote the top and bottom elements in the lattice. And we use this because using the meet operation, we can have a node having more than one type, and which is what is expected in graph databases. And we also use the top when a query is, when in a query we don't know exactly what is the type of some element of the query. For instance, an edge. If we don't know what would be the type of the edge, we can just use some symbol representing the top of the lattice. And then, in addition, so we have that the edge types is also a poset, a partially ordered set that includes the basic types that we have given, and a top element. So this, in this case, we would have a flat poset. And again, in this case, the top is just for having the possibility of defining queries where the type of some elements have not been defined in the query. Then the types of value nodes are the source of in the given algebra. So we assume that we have a given data algebra in our database, and the types of the values then are the source of this given data algebra. And the types of the edges representing attributes or properties are just the names of these properties or attributes. So then a type graph is this kind of, it includes this kind of set of nodes, this kind of set of edges, and as usual, source and target functions. And typing morphisms are standard kind of type morphism with the slight change that the usual equality, homomorphic equality that we have with source and target with respect to typing, in here it's converted into a small or equal, so to have inheritance. This is something that was used already in a paper whose authors were Ulrike, Golas, Lin, Hartmut, and myself 10 years ago or so. And, and then also, and then in addition, the typing of every node value should be the sort of the carrier. So for any value, V should belong to the carrier of the sort of that value. Well, in addition to graphs, so these graphs would be the models that we would use when presenting as a model for a graph database. But in addition, we need to work with some patterns that are the basic ingredient for defining formulas in the case of the logic, or queries in the case of the query language. So these patterns describe partially, in a way, a graph. So they consist of a type symbolic graph, and in addition of a set of path expressions. So the pattern, the fact that it's a type, the pattern includes on one hand a graph G, a type symbolic graph, and a symbolic graph, in case you don't know what it is is just a graph, G, an attributed graph, where the values are not really values but variables, and where a set of constraints of really equations describe some properties and including the values of some of these variables. And then path expressions are specifications of paths that we assume that should exist in our pattern. They consist of two nodes, so the source and the target of the path, and of a regular expression of edge types that describe what is the shape of the path. So, for instance, here you have an example of a pattern where we have three nodes, N1, N2, and N3, which are supposed to be airports. And the cities close to this airport of X1 is Los Angeles, of N2 is London, and N3 is Barcelona. Here we have the attributes. Instead, as I said, instead of values, we have variables. Here we have also the attribute of price for this edge of this flight. And in this case, so these equations tell us precisely that X1 is Los Angeles, so the city of N1 is Los Angeles, the city of N2 is London, that X4 is, which is the code of Los Angeles, is LAX, of the code of N2 is London Heathrow, and the code of X is BCN. And in addition, there's a terminal here, which is terminal 1. And in the case of the price, we don't have any specific value given to the variable, but only a property saying that Z, variable Z, is smaller than 500 euro. And in addition, we have this expression, this path expression that says that this connection should be a path consisting of some number greater than 0 connections of flights and shuttles between N1 and N2. So it would consist of a sequence. Any path that would match this path expression would be a sequence of flights and shuttles between airports and terminals, probably, of the airport. Okay. Patterns actually can be seen as a generalization of the kind of type property graphs that we have defined, in the sense that in that case, the variables we may consider that all variables are given the value that the attributes of the graph have as, and the path expressions of the graph is the empty set of path expressions. So in a graph there are no path expressions. So any graph may be considered as a navigational pattern. By the way, so here we are, this fact of using variables all over the place is actually a technical decision. So we could allow for having directly some values instead of variables, and mix variables with values. And so, for instance, in here, X1, X2, X3, etc., could just be, instead of them, Los Angeles, LAX, etc. But Z, we would have the variable Z anyhow, just to say that Z is smaller than 500. The reason why we have all these variables is because technically it's simpler to consider that everything is a variable than considering that we are mixing variables and values. And so we have morphisms, and a morphism between patterns is just a graph morphism, a symbolic graph morphism, such that path expressions are in a way preserved. More precisely, mean that for every path expression that we have, P is the set of path expressions of these two patterns, P and P prime. And so for every path expression in P, there should be a path expression in P prime such that the language defined by alpha prime is a sublanguage of the language defined by alpha. So this is a kind of refinement. And so since graphs can be seen as patterns, path expressions can be seen as pattern morphisms. Graph morphism can be seen as pattern morphism. This C that I have here is because actually we don't take here P prime, but what we call the completion of P prime, which includes also path extended with edges that exist already in the graph. Okay. So let's now go into queries. And let me tell you what a query is, what means a query as a formula, what is satisfaction of a query as a formula, and what is the semantics of a query as really a query, which it would be the set of correct answers for the query. So queries, the most basic kind of queries are what we call atomic patterns. So these patterns consist just of a node with maybe its attributes, of an edge, or of a path expression. And so that would be the way we represent the query, sorry, the pattern. This would be the way we represent the patterns internally as patterns, and this would be the syntactic way of the way we see it syntactically with some syntactic sugar in the query language. And so this means that these atomic patterns are just represent searching for a value, searching for an edge, or searching for a path. In addition to these basic queries, we have a more kind of, so to say, complex queries. So on one hand, if we have a set of queries, then the conjunction of this set of queries is already a query. So a conjunction is represented in here by commas. Then nesting, and nested, if we have that Q is a query, then we can add it some nesting. And so Q with a nested query, big Q, is also a query. So in general, queries are nested, like in formulas in the logic. And in addition, if Q is just a basic query, but only a node or only an edge query, then not Q is a query. So this means essentially that compared with GNL, with the logic of navigational graph, this set of formulas or queries is a fragment of the formulas in the logic, where essentially the idea is that here we represent formulas that with at most 2 levels of nesting. In principle, we may have more, but they could be reduced. So it's equivalent to 2 levels of nesting. The main difference concerns negation. So negated queries cannot be nested, and we cannot negate a query that asks for a path expression, because this would be very difficult to implement in a real database. Actually, in query languages, they don't have negation of queries for negating paths, the existence of paths. So in general, a query is of the form, we have a pattern P1 with some additional nesting, Pi with some additional nesting, and then not Pi plus 1, not Pn. Well, all these P's are patterns, basic patterns, atomic patterns. So solving a pattern or satisfying a pattern, which is essentially the same, in order to define it, we have to take into account several things. So the first one is that in a pattern, every element, so every element meaning a node or an edge or a path expression, well, not a path expression, every node or an edge or a value or a variable is a logical variable. And so when we want to solve a pattern, then we must define a matching of from the pattern to the given graph G or to the database that we have. So in this way, we can give value to all these patterns by matching the nodes and edges, node and edge variables to the elements in the graph database. Well, since our graphs and our patterns have some constraints because they are symbolic graphs, then the data algebras should satisfy the constraints as translated by the matching morphism. And in addition, for every path expression in the given pattern, there must be a path in G such that P belongs to the language of A, so that matches the regular expression that we have in the path expression. Okay, so this is satisfaction of a pattern. But satisfaction of a query, even if it's atomic, is slightly a bit more complex because in general, we cannot just define in an isolated way whether a given query is satisfied or not. The reason is because the query may be included in some kind of context. For instance, maybe part of a conjunction, and this query may share some variables from the other queries in the conjunction, and so this would constrain the possible values of Q, because the matching Q would affect the matching of Q on Qn. So in order to deal with this issue, we define satisfaction of queries in a given context. So, and which we will define in a minute. But in order to define this notion of satisfaction, there is a specific kind of context that plays a special role there. That is what we call the global context of a query. So if a query is P1, if Q1, Pn, Pi if Qi should be not Pi plus 1, not Pn, then the global context of this query is a constraint that is just the union of these constraints P1, Pi. Then with this notion of constraint and given a context Q and a morphism from the context into G, we may define satisfaction of queries as follows. So this G satisfies P if Q in a context Q with a matching M if there is, and so here we can chase this small diagram, if there is some matching from Q union P into G, such that if this is the inclusion from Q into Q union P, this diagram commutes. Then for negation is what one would expect. G satisfies not P in context Q with respect to matching M if there is no M prime such that this thing happens. For a conjunction, we have that if Q is a conjunction, we have that G satisfies this conjunction in context Q with respect to matching M if there is an M prime going from Q union Q in the global context into G, such that this diagram commutes, where A again is the inclusion from Q into Q union Q, Q sub Q. And in general, given a query Q and a graph G and some matching M, then is G satisfies Q for this matching M if it satisfies it for the empty context. Now, we could think, in general, we consider, so this is, I have just defined what it's, so to say, the logic of queries. And now we are going to see what are the answers to a query, what is the semantics of a query. And so the semantics of a query is a set of correct answers, and an answer to a query Q in particular, a correct answer, is a subgraph of G, some subgraph of G, so that the database, if G is the database, satisfies Q. The issue is that not all subgraphs of the database such that they satisfy Q can be considered a correct answer for Q. First of all, because of negative queries. So it may happen that some negative query is satisfied by the database in total, but not by some subgraph. To say it in a different way, a subgraph may satisfy a negative, sorry, actually it was said in the wrong way. A subgraph may satisfy a negative query, but maybe a bigger graph, in particular the database, may not satisfy that negative query. This is one reason. The other is that, besides this question, we are not interested in all graphs that in a way satisfy, taking care of this negation. Not all graphs, all subgraphs of the database are reasonable to be considered a reasonable answer. For instance, the database should not be considered a correct answer because it would be an answer too large. So actually what we want are minimal graphs that provide the right answer. And this is done by assuming that an answer should include a path assignment, that is a mapping from the set of paths of the given constraint or from the given context to the set of paths of the graph database. And in addition, they should include, the answer should include the matchings for all node and edge variables, obviously. But in addition, as I said, the graph should be minimal. A minimal graph, assuming some minimal graph with respect to including all the graphs assigned by the path assignment, all the paths assigned by the path assignment, and all the node and edges matching, which are assigned by the given matching. So altogether, this is like saying that if we have the morphism N that matches the given context query, if we take the global context associated to the query, if we enrich this global context with all the paths that are assigned by F, and we get an extension of this morphism into the graph database, then the right answer, the correct answer, is a graph G, where this is the epimono decomposition of M prime, which ensures that this is minimal and include the images of everything. And well, as an example, although we are not going to pay any attention how this is. So if we have this, if this is the global context defined by the query that we saw at the beginning, then these three graphs would be correct answers for that global context, and so for that query. And now Elvira should continue with the operational semantics.
Okay, can you hear me? Yes?
Yes.
Okay. Let's see. Good afternoon. After the presentation of Fernando, now I'm going to present the operational semantics we have defined for our language of queries to graph databases. And to do so, for this purpose, I will take the same example of query that Fernando has already used. And moreover, I'm going to use a graphical representation with the idea that the expressions can be followed at a glance easier. Okay. Before getting into the subject, I'm going to summarize the most important things from the previous part that explained Fernando that we need to keep in mind. First of all, we have to recall that that we consider all the elements in a pattern are variables or are undefined. For instance, another is that the variables are variables, but even types and path expressions are part of the pattern that are undefined, and we have to follow for an instantiation into the graph database to have a solution. This is an important idea. Then, as Fernando says, we have positive and negative patterns that are existentially quantified logic literals. So, solving a pattern will mean finding a matching that evaluates the variables into the graph database, so the literal can be satisfied. So, solve and satisfy is the same concept. You have seen that queries are conjunctions of literals. So solving a query or satisfying a query, what we mean finding a matching that satisfies all its literals. And finally, it is important to recall and to have in mind that the answers in this case for these kinds of languages that query graph databases are graphs. The answer is a graph. In particular, is a subgraph of the graph database that instantiate all the variables, all the undefined parts of a pattern, and that pattern is the global pattern that Fernando have introduced before. Okay. We can look at this at a glance because Fernando already have already explained this example. We have here the query, the global context, and some instantiations of the global context. The three above are correct answers, but the last is not because this instantiation is a correct instantiation of the global pattern. It's a subgraph of the graph databases, but it doesn't satisfy the nested subquery in the fourth literal of the query. Okay. So let's go now to the operational semantics. First of all, we have to say that our proposal is inspired and based directly in the usual definitions used in logic programming, specifically in constraint logic programming, where computing, specifically an operational semantic, formally defines a bottom-up process, which is a refutational process for computing the answers, where computing answer means finding an evaluation, the same as before, for every variable and in every literal of the query, such that it is guaranteed that all this matching, and this is an important question, agree each other. So the operational process match everything in a way that all the matchings agree each other. Okay. Another important thing to take into account is that as language, the nested subqueries define new inner scopes of visibility. This implies that the variables of the nested subquery must be solved to satisfy the query, but they don't contribute to the construction of the answer, to the graph that will be the answer. Finally, we have to prove equivalence of the logical and the operational semantic to guarantee that every computed answer can be proven to be logically correct, and that every logically correct answer can be effectively computed. Sorry. Let's now to be a little more specific in describing how the answers are computed. First, computed answers are built as a final state of derivation, okay? Where a derivation is a refutational process defined as a sequence of state obtained by solving a step by a step every atomic pattern in the query. Specifically, at every state of a given derivation, an atomic pattern is selected and a reduction rule is applied to try to solve this pattern. If the pattern is solved, then it can be removed from the list of literals that are waiting to be solved. Okay. If the selected literal is navigational, we have to apply, in addition, an unfolding rule, and after that, we can try to reduce it. As I said before, in every step of this process, we must guarantee the property of agreement of all the matchings that we are using to solve the atomic pattern. Finally, we say that the derivation is successful if every atomic pattern can be reduced after a finite number of steps of derivations. More specifically, talking about the state, and a state consists of a list of literals that have to be solved, or that are waiting to be solved. In the initial state, we have all the literals of the query. And in addition, excuse me, we have two bindings. On the one hand, C is a set of constraints that bind every solved variable to a specific value into the graph database. This C is very important, and it is needed to be able to guarantee the agreement, the property of agreement of all the matchings performed along the derivation. Okay. On the other hand, in the state we have this Q, which is a pattern. We call the current computed context, or the current computed pattern, and it's a refinement of the global context of the query that has been obtained by the application of other rules, as I will see in a moment. Okay. If the derivation is successful, then the final state is such that the list of literals is empty, of course, because we have solved every literal, and the final psip, this psip F, contains a constraint for every of the variables that appear in every of the pattern of the query. Everything is solved. I mean, and QF is like a pattern of the final of the solution of the answer. In the certain is like the global pattern, the initial pattern, but where every path has been instantiated by a concatenation of edges. Then the final answer can be computed by instantiating the final pattern QF accordingly to the CF. Okay, to do so, to build derivation, we need derivation rules. Okay, as I said, we need to define two types of derivation rules: derivation rules for non-navigational literals and unfolding rules for navigational literals. Let's see. Deduction rules, as I said, are the sample rules for non-navigational literals, where reducing a non-navigational positive literal, that is an atomic pattern, means first finding a matching to the graph database satisfying the property of agreement in a given state, and if exists this matching, that is, if the atomic pattern can be solved, then we can remove the pattern, the literal, from the list of the sequence of the literal that are waiting to be solved. We said that it is reduced. Okay, if the literal is nested and the outermost pattern can be reduced, then the nested subquery has to remain in the sequence to be solved in a sequence state. And on the other hand, to reduce a negative literal, we only have to check that there is not a match satisfying agreement. So we can eliminate it from the list, and that's so. In this slide, we can see the more formal writing of the rule, but also a visually one. I center in the visual one. It's easier to understand. The idea is that example in green we have the literals that have already been solved, and in blue we have the selected literal in a state. This down represent a given state with a part that has been solved and another and a literal that is selected. On the right we have the graph database, and with the representation of the matchings that can be used as a solution for this specific situation. Okay. Let's see in the negative case. Okay. Rule 2 rule R2. Okay, in the same way, here in the down, we have that the last negative literal is selected, and all the previous literal are supposed to be solved in this state. So at the right in the graph database, we can see that that after checking that this forbidden connection, these forbidden connections doesn't exist in the graph database. Specifically, this means that from this airport to Barcelona, we can go without using this forbidden, or this it doesn't exist, this forbidden connection. Then everything is solved, and we have the final solution. Okay. Okay, let's see the unfolding rules. They are a little more complicated, and we need it when the literal selected is navigational. The first one is to say what does mean unfolding, and what we want to say when we apply an unfolding. Okay. Applying unfolding rules for us means replacing the pattern by one of its unfoldings and trying to reduce just an age, this age. Okay. Be more specific, to define unfolding of a pattern, we need to use the following property of regular expression. That says that every regular expression can be uniquely decomposed, as can be seen here. That is, there exist two sets of symbols, S0 and S1, such that S0 contains of the words of length 1 of the language defined by the regular expression, and S2 contains the starting symbol of the rest of the words, so the words that has a length greater than 1. Okay. These properties allow us to define two kinds of unfolding. The first one consists on replacing a navigational pattern, path pattern, with just an age, a unique age. And the second kind of unfolding consists in replacing the path pattern by an age followed by another path pattern. Okay. This allows us to define two kinds of unfolding, one for each kind of unfolding. The first one is the rule U1. In this case, which correspond when the replacement, when we replace a path pattern by just one age. And okay, note that the rule works as follows. The navigational pattern here in blue and here in the example is replaced by a single age, and then is this age which is reduced by finding the corresponding matching. And if there is a nested literal, then this remains in the list. Okay. The rule U2 corresponds to the second kind of unfolding. And in this case, the rules work as follows. The navigation pattern is replaced by an age followed by a path pattern. As I said before, this is the age and this is the other path pattern. The age is reduced as before, and the new age pattern remains in the list of literal that are waiting to be solved. Okay. Okay. To end, that finally say that we have proven the equivalence of the logical and the operational semantic. That means, as I said before, that every computed answer is logically correct, and every logically correct answer can be computed by a derivation, as long as the criteria we use to select the literals satisfy the property set fairness. It's fair. That essentially means that every literal is going to be selected eventually. Okay. Now that's all. I turn the control back to Fernando to go to the conclusions.
So to conclude the talk, what we have presented is these kind of graphs to represent the databases and the queries. And we have defined a language of queries as a fragment of the language of GNL. And we have defined as semantics and an operational semantics that we have proved that are equivalent. So there are several ways to continue this work. The one in which we are working now is to extend the language with paths as first-class citizens, and this means allowing paths to have properties or attributes, and also to define specific constraints about paths. Like, for instance, that if we have a sequence of flights, then the departure time of a certain flight in the sequence should be greater than the arrival time of the previous flight. This is almost done, this kind of work is, so everything seems to fit well. And afterwards, we plan to try to see how we could handle extra logical constructs. So in our work up to now, we deal only with logical constructs, but not with constructs like counting constructs, saying how many queries, like how many connections there are from Barcelona to Paris, for instance. We also think that it might be interested to deal with transactions and satisfaction of integrity constraints using GNL for describing these constraints. And something that we also think that might be interesting would be trying to find an algebraic formulation, in the same sense that for relational databases we have the two kind of formalism for foundations, the algebraic and the logical formalism to define the semantics of the databases. And well, thank you for your patience and for listening until here. And if you have questions, we will be happy to answer.
Okay, excellent. Thank you very much. Yeah, so thanks for the nice talk, Fernando and Elvira. So was there a hand just there? I can't see it. So I have a question. Maybe I make a start and then we can sort of see who else wants to chip in. So you explained that the structure of the queries is restricted in the sense that you have essentially literals, positive and negative literals, and then combinations of them, and then one level of nesting.
Yeah.
Yeah.
Mm-hmm.
And that sounds a bit like clauses in programming, obviously. So I wanted to understand if this is the same, or what does it mean for the expressiveness? Is this actually full first order logic, but just represented in some kind of format that makes the reasoning easier, as I said, like clauses, or is it actually limited in the? I mean, presumably the level of quantification is limited, isn't it? Because you cannot have alternating quantifiers.
We cannot have alternating. So we can have alternating, but just one layer. in one level of nesting. So we may have a positive query, and inside this positive query, a negative one.
Okay.
Or we may have several levels of nesting, but all of them positive, which we know that it's equivalent to a single level.
Yeah. Okay. So that's what you mentioned.
Yeah.
With the flat.
It's close to closest, but the main difference is paths, dealing with paths.
Yeah. Okay.
Because dealing with paths means having to use some kind of, at the operational level, to have some kind of procedure to deal with the inductive definition of paths, which we use the unfolding rule for doing this.
Yeah.
We may have non-termination there. In clauses for a finite database, every query will terminate if it's positive.
So that was my next question. So if you have this limitation, normally in a normal sort of normal, but there's this notion of safe SQL query, I think, which basically makes sure that they always terminate. But you don't have anything like this here.
No, it may. So it's like in logic programming, the answer, there may be an infinite number of answers.
Yeah.
So if one thinks of that the execution could be like in the case of a logic program, you get answers and answers until you are fed up of getting answers and say, okay, stop. That would be the idea. Because in general, we don't have in practical languages, you may ask for having not repetition, and so this probably not repeating an edge or not repeating a node, and this probably adds a limitation on the number of gives some finiteness to the number of answers. We could have this limitation in this additional work that we are doing now, because one can ask as a constraint that a path does not include two elements which are repeated or something like that, and then one. The problem that is that from people that have studied, as I say, complexity of graph databases and query languages has been quite thoroughly studied by a number of people. And if you want paths without repetition, then this is computationally more complex than if you don't ask for that requirement.
Okay. I mean, I know in my last comment, and then maybe I'll leave it to someone else to ask a question. So I know, I mean, about path expressions, for example, Groove has path expressions.
Sorry?
Groove, the tool, has path expressions, and they can actually be negated. So they have sort of positive and negative conditions, and they can mix them into path expressions as well. So it's not a question, but obviously it's not a question about whether you can evaluate this or not, but it's a question of complexity.
Well, there are two issues with negation. So one is not allowing to have nested negated literals. So if we would allow this would mean that we would allow any kind of alternations in the nesting, and this we know that this would be at least its expressive power would be at least as first order logic. And so this shouldn't be the case. Now the other issue is whether we can allow negating a single literal, but including a path. In this case, the problem is the computational cost, because this would mean looking through all. I guess I'm not completely sure, but at least this would be a problem. Looking whether you have there is no connection between two cities, for instance, it may mean searching through all the database in some complex way, and so actually, as I said, query languages don't include this possibility, just because they have seen that from a practical viewpoint. It was too costly.
Okay, good. Thank you. Any other questions? I heard that we have some graph database experts here. So maybe then I have another one. I had one on the counting, so I found that interesting. You said there's a there are variants, or you're considering variants where you can count.
Yeah.
Basically solutions, right? So
Yeah.
you have a formula that doesn't evaluate to true or false, but to the number of solutions you find.
Yeah.
Is that what's?
Yeah, well, in graph databases, you have these kind of constructions which are non-logical, and actually also in relational databases, you have also these kind of constructions. But the people that deals logically with relational database separates this from the logical aspect. And so in here, so we have not considered them because actually from a logical point of view would mean going from something which is semi-decidable to something which is I don't know what level of non-computability would be in general. But nevertheless, there could be reasonable. We think that there could be reasonable solutions that, in a way, represent some kind of these constraints, because there are several kinds of these kind of constraints, like counting, as I said. But there might be other possibilities. Although dealing with paths as first-class citizens, I must say that some conditions that could be difficult to deal suddenly become simple, in the sense that, for instance, suppose that we have an example that we want to have a connection with several flights from Barcelona to Los Angeles. In the current framework, we cannot express that the total cost of the trip is smaller than, say, 2,000 euros, because this would mean not counting, but adding the value of each element of its edge, its flight that we have in the path. And again, this would be extra logical. But if...
Sorry, why is that? Because you don't know which elements are in the path, basically.
Yeah, basically, yeah. But if one is able to define attributes on paths, and we know how to do that now, then one can define the attribute cost of the flight, and also arrival and departure times and things like that, and then we can say that the total cost is smaller than 2,000. And the main idea for doing that is defining the attributes in terms of unfolding. So if we consider that a path, the possible unfoldings of a path, then we know how to compute this attribute in terms of the unfolding. And so this means that for each unfolding, we have a set of equations that would be part of the equations of the constraint as the other equations that we already have. And, I don't know up to which point some of these extra logical constructions could be solved in a similar way, but so I think this might be interesting.
Certainly sounds like a useful thing to have, and but I can see that this is beyond. I don't even know if it's monadic second order. I mean, normally talking about paths is monadic second order, but I have no idea what monadic second order combined with sort of full first order logic means, with those handling of attributes and things like that. But yeah, anyway.
I don't know.
All right. Yeah, Nicolas.
Thanks a lot, Elvira and Fernando, for your nice talks. Very interesting. I was just wondering if you could comment a bit on this algebraic approach to these graph databases, because I'm wondering, are you alluding to a possibility that, because I mean, once you have the carrier set of such a graph database, I mean, that is some sort of graphical structure which you could rewrite, of course. So I'm just wondering, is there any work on, because you could imagine that a typical graph database would be changing all the time because it is maybe reflecting some data stream or something like that. And I'm in particular interested, so is your idea for what, I mean, could be a direct derivation, I'm thinking the way you described it, that you have for each graph database and for each set of queries, you have the solution. So there's some like a vibrational structure. And then when you rewrite the carrier graphs or the graph database itself, you of course change all of these occurrences potentially. But I mean, you might have some notion of update, let's say, where you some preserved parts and some. Is there any work in this direction you are aware of?
Well, so what we have in mind is two kinds of things. So one is very generic. So in relational databases, you have that queries, and you can define them logically with the relational logic, or with algebraically, and there's a direct translation from one to the other. And actually, this is good because the logical form of the query, if it's translated to the algebraic form, then this is easily to implement in practice. So we think that having something like that would be nice. So that's something algebraic. On the other hand, there's the issue that concerning transactions. So in transactions, we may want to add elements to the database or delete, and then would be including graph transformation, therefore, for doing addition and deletion. And that then one would want that if there are some integrity constraints, be able to check that the integrity constraints are satisfied. So concerning if we know if anyone is doing something like that algebraically, though we know that Dominique Duval and Rashid Eshahed and also some other co-author are dealing with graph databases. Mainly they work on RDF, but I don't know if they have gone into also property graphs algebraically. But we haven't studied in detail whether this could be the way and that we could combine or not. So we know they have some year ago or 2 years ago, they presented something at GCM, and I think they have also presented something for ICGT this year, but we haven't looked at it. So we don't know exactly what they are. Well, I remember what they did in the GCM paper, but this was not, this was very basic. I don't know what they are doing now would be along the lines that we have in mind. If it is, well, then it would be nice to work with them and try to find some kind of common framework or so.
Thank you.
Yes, Andrea, you are muted.
Thanks, Elvira and Fernando, for the nice talk. I wanted to ask just something related to your choice of formalization of this property graph database. Because, okay, you choose a specific formalization using typed attributed graphs with inheritance on type nodes and so on. I imagine that this choice was based on the current use of this structure in graph databases. My question is whether with this choice you feel that you considered essentially all the structure that you might find in this kind of graph databases, or if it's also a compromise between what you find and tractability, so you know how to handle these, but there is some feature in real graph databases that you don't capture well enough, and that could require more work.
Well, actually, in graph databases, there is no inheritance, or at least that we know. Or maybe there is some place, but for instance, they don't. So one of the issues that people in graph databases study, and there are some proposals, is to have what they would call a schema in the area of the databases. That is what we call a type graph, a schema. And so in graph databases, there are no schemas. Only in RDF databases, there is a schema. There are schemas, but not in general, not in property graph databases. So in this sense, what we are presenting extends the language by allowing to have inheritance. What they have is some peculiarities that we can handle with with our notion of subtyping and inheritance. So one is having several types for a given node. So we're having this meet operation in the lattice of types, of node types, then we handle this without problems. And the other is that you allow queries where some of the elements of the query are not typed. Mm-hmm. You say, I'm looking for a node. I don't mind which type it is, whose ID is that one. And then, for instance, you imagine you have a movie database and you have the ID of someone and you don't know if it's a director, or an actor, or a producer. And then you are looking for a person who has that ID, but you don't know the type. And so on this we can handle very simply, having a top element that describes in a way the absence of type, or because any type can be possible. So at the level of types, we can handle everything that it's used in practice. And in addition, we have inheritance. So we allow subtypes between the basic types and subtyping and inheritance. Our main limitation with respect to is this non-logical, this extra logical operation. So in a graph, in the real languages, like Cipher or this kind, so they have counting or other kind of constraints that are operations that are done in between the query, part of the query, and we don't have this because these are extra logical. This is what we cannot handle. The rest, if I'm not wrong, that I'm almost sure that we are not wrong, we can handle without problem.
So, but this is in the query language, basically.
Yeah,
not in the structure of the database. So you capture essentially all the features of the database. Okay, thanks.
Actually, we were even thinking having inheritance on edges, but this showed to be a bit more difficult, especially especially with respect to the path expressions, because so if you have inheritance between edges, then a path that includes some edge should also include its subtypes, and some kind of it should include its subtypes, and this makes a bit of not terribly difficult, but at least messy dealing with paths when you have edge subtyping. And it's not really clear whether this is any useful. That's another issue. So if it's not useful and it's complicated, then it's better to forget about it.
Okay, good. Any other questions, comments? Okay. So then I suggest that we close the official part of the seminar and we can stay here and we'll continue to chat, but we will disconnect from from YouTube. So thank you very much again for the nice presentations. I certainly learned something about query languages for graph databases. And I don't know, Nicholas, you want to say something about the next?
Yes, so again, also from my side, thanks a lot, Elvira and Fernando. And the next talk, because in 2 weeks will be Easter, so we will have another talk in about a month's time by Uwe Wolter. This time it'll be a bit of a special format. There will be a pre-course of about 1 hour on the mathematical theory of sketches. And then he will tell us in the second part, the actual talk, about how sketches can be used in graph transformation. So it's going to be like a little bit of a special issue of GReTA in that sense. And that will take place on April 21. Yes, so thanks a lot. And I will now disconnect the YouTube. If anybody's still there and wants to meet us here for a bit, do come over to Zoom.